we are going to discuss unit 5th, temperature distribution in solids and laminar flow. So first we will discuss convective transport of energy. So when the energy transport due to the bulk motion of fluids is called the convective transport of energy in simple manners. Okay, so here we are considering three mutually perpendicular elements of area ds, of area differential area ds or ds1 at point V, where the velocity of fluid is considered v. Okay, so you can see in the figures these planes are made by liquids, mean these are liquid planes. Okay, so for first case, volumetric flow rate equals to Vx ds, where Vx the velocity of fluid in x direction and ds is the differential surface area. So we can calculate a volumetric flow rate for y and z component as well. For y component it will be Vy ds, and for z component it will be Vz ds. Okay, and next we will calculate the rate at which energy is being swept across the same surface element or transfer from one to another point. So for our first case, when fluid is flowing in x direction, then this energy equation will be equals to 1 by 2 rho v square plus rho u where it goes Vx ds. So first term represents the kinetic energy, second represents the internal energy, and Vx is the velocity of fluid in x direction, ds is the differential surface area. Okay, so we can write this for all coordinates, for y and for z. So the overall equation we can write in 3D coordinates, 1 by 2 rho v square plus rho u where it goes del x Vx, where del x, del y and del z is the unit vectors. Okay, so first part represents the x energy flow in x direction, second represents the energy flow in y direction, third represents the energy flow in z direction, equals to overall half rho v square plus rho u where it goes vector v. So this is the overall energy in all the directions. Next, work associated with molecular motions. So when the fluid flows from one point to another point or from minus to plus side, then it has the velocity. Okay, so the work is done by the fluid from flowing from minus side to plus side equals to phi x dot v ds. Okay, so phi x is the stress vector or tensor, v the velocity, and d is the differential surface area. So similarly we can write two other components as well, like pi y v ds, pi z v ds. Okay, and in expanded form we can write the rate of work expression per unit area becomes like first pi x tensor dot v vector equals to pi x s vx plus and so on. So this is for x component, second for y, and third for z component. So these three equations we can write into a single equation in a vector or tensor form. Okay, that is work flux equals to tensor pi dot vector v equals to del x bracket pi x dot v plus so on. Okay, so this is the final equation. Next, here we are writing a combined energy flux which is shown by E. So combined energy flux equals to half rho v square plus rho u bracket close v bar plus pi dot v plus q. So first term indicates the convective energy flux, second indicates the work done per unit area by molecular mechanism, and third rate of heat transfer per unit area by molecular mechanism. Okay, so overall summary is given below: convective energy flux vector, molecular heat flux vector, molecular work flux vector, and combined energy flux vector. Okay, for first in which we consider internal energy, and second case we consider enthalpy here. Thank you.